Hello everyone, in this lecture we will be solving a 1998 St. Petersburg City Math Olympiad problem. Here's a view of this problem. Let n be a positive integer. Show that any number greater than n to the fourth power over 16 can be written in at most one way as the product of two of its divisors having difference not exceeding n. So what I will do instead is to write an equivalent statement, equivalently, and I will go ahead and prove that equivalent statement. So suppose we have integers a, b, c, d ordered in the following fashion with the property that a times b is equal to c times d, which is equal to n. Obviously a, b, c, d are divisors of n, and it is possible to write n in two different ways, and the fact that b minus a is less than or equal to n as well, so still not exceeding n, the difference of two of its divisors. In this case, if b minus a is less than or equal to n, it would suggest that c minus d is also less than or equal to n. So in this case, we would like to, well, first of all, we claim that, so this, if this is true, then all I will show, then show that basically n is strictly less than n to the fourth power over 16. So I claim that this question is equivalent to the following form using just simple logical argumentation. So given this fact now, let's start with the following observation. Observe that, well, first of all, if you look at the following difference of squares, a plus b squared minus n squared, that's definitely less than or equal to a plus b squared, minus b minus a squared, and this inequality follows from this condition here. But notice that this is simply equal to 4ab after you expand these squares, but recall from the given condition that 4ab is equal to 4 times cd, c times d, and 4 times cd can be equivalently written using a similar trick we did for a and b, c plus d minus, I believe d is greater than c, so d minus c squared, but that's obviously less than or equal to c plus d squared. So this is kind of a simple observation, and therefore we can conclude that if we move that n squared to the right hand side and then this c plus d squared to the left hand side, we have the following form for the difference of squares. So let's keep that in mind for now. In the meantime, I make the following claim here next. I claim that if a, b, c, d are ordered in the following fashion, then it must be the case that a plus b is greater than c plus d. And the proof is actually not too hard. So all we need to consider is the following function. So consider the function f of x equals x plus n over x. And why should I consider that? Because this inequality that we would like to prove is equivalent, given this condition here, to a plus, I can simply replace b with n over a, and therefore all I want to show is that c plus and d can be replaced with n over c. So therefore all I need to show is if a is strictly less than c, then it must be the case that obviously this is f of a and that's f of c c, so suggesting that our function f is a decreasing function. But that kind of follows immediately, for instance, from the shape of this function f. Obviously, let me draw this briefly. So it consists of two parts. Y equals x is probably the 45-degree line like this, and then we are adding a hyperbola here like this. So therefore, when I add these two, I should get roughly this following shape. And obviously this shape will have its minimum probably at this point here. Oops. Yes, right at this point. So therefore we can find this point easily, for example, by just taking the derivative of this function. So we would get, and setting it equal to 0, that would suggest that so f prime of x, well, that's simply equal to 1 minus n over x squared. And as I said, setting this equal to 0, we would get that for x strictly less, yes, so strictly less than square root n, our function is in fact decreasing, as you can see in that range. So that's square root n here. Obviously I will have negative values for x strictly less than square root n. At exactly square root n, that would be exactly equal to 0, obviously. So therefore this inequality is true because we just have shown that our function is a decreasing function. F is decreasing, here. So because f is decreasing, if a is strictly less than c, then it must be that f of a is greater than, strictly greater than f of c. And that obviously proves the claim, because f of a is a plus b, n over a is just b, and similar f of c is just c plus d. Now going back to where we left off, namely this rectangular thing here, let me open a new page and follow on a new page. So far we know these two results from our analysis so far from the previous page. So therefore now let's start with this first result here. Let me just write the right hand side first. So n squared is greater than or equal to, I can replace a plus b knowing the second inequality now. So a plus b is at least c plus d. So therefore, and more actually, because this is a strict inequality, so it's at least c plus d plus 1. So I'm replacing a plus b with c plus d plus 1 squared, minus, we still have c plus d squared here, but that's simply equal to 2c plus 2d plus 1. Now it's time to use AMGM by the arithmetic mean, geometric mean inequality. We have that n, which is equal to c times d, obviously, that would be less than or equal to c plus d over 2 squared. We know this by the AMGM inequality here, but then that's less than or equal to, using this condition here, obviously c plus d from here will give us that n squared minus 1 over 2 is greater than or equal to c plus d. Therefore I can replace c plus d with n squared minus 1 over 2, but then I have another over 2 and then a square, so therefore what I will get is n squared minus 1 squared over 16. But that's obviously strictly less than n to the 4th power over 16, and that's exactly the bound that I needed for my proof. So therefore, whenever we have the numbers, the divisors a, b, c, d of a positive integer n, such that ab is equal to cd, a times b is equal to cd. Moreover, where b minus a is less than or equal to n, or in a similar way d minus c is also less than or equal to n, then it must be that our number must be strictly less than n to the 4 over 16, and that solves our problem. Hope to see you in our next video.